Cool. Welcome everyone to our Algo Hour. It's been a while since we have like a public or external sessions. And yes, even our external speakers get to choose their walk-up music. So another motivation to sign up to speak at a future Algo Hour. So we have Alessya and Jamie from whylogs today. And before we get started with the talk, I want to give a special shout out to Natalia, Elijah, and also Ramandeep for connecting us with Alessya and Jamie. And I'll let Natalia do an intro for Alessya.
Yes, great to welcome Alessya and Jamie here from whylogs. So I met Alessya a couple of years ago. She's now the CEO of whylogs, which is an AI observability company that builds tools for robust and responsible AI. And when I met her, she was a CTO in residence at the Allen Institute for AI. And I was really kind of blown away and very motivated by her vision for something that's incredibly necessary in the ML space and for observability. Really excited to keep following whylogs and where they have gone. And Alessya is also the founder of R2 AI. It's a global community of AI practitioners. Really a great person for community organization in the AI space, and gives a lot of great talks. So I'm excited to particularly have Alessya and Jamie here because we're integrating, or by we, I mean the model lifecycle team is integrating whylogs, the open source library that whylogs has created, and Alessya and Jamie will present today. This is a data monitoring library, so this will be integrated with Kudu extracts and available for folks at Stitch Fix who use Model Envelope and Kudu. So on that note, very warm welcome to Alessya and Jamie. Take it away.
Thank you. Thank you so much, Natalia, for such a wonderful introduction. And thank you, Tianlin, for hosting us. The challenge with picking up the entrance music is if you pick something super upbeat, then you have the challenge of like following that with the energy. So I'm going to do my best. Thank you so much for having us over. I'll take a second to let Jamie also introduce himself, and then we'll kick off with our presentation.
Yeah, hi, thanks for having us. My name is Jamie Brumal. I'm a developer here at whylogs, and I lead the team that maintains whylogs, so our open source projects.
Jamie is very humble, but I'll leave it at that. I'll let him demonstrate his skills in the live demo that we prepared for you. So as Natalia already highlighted, I'm going to share my screen really quick. We would like to talk about. We would like to spend this hour talking about large-scale data and machine learning monitoring using a library, open source library called whylogs. And special thanks to, actually, I see a few people here on the call, Ramandeep, and I think Elijah, I might have seen him earlier, and Natalia, and especially Ramandeep for contributing feature requests, suggestions, and a lot of kind of trials of the whylogs library that inspired the current 1.0 version of the library that we launched. With the involvement of the community and feedback, like the stuff that we get from Ramandeep, the library just gets better and better. And we're super excited to tell you a little bit about the history of why we're investing time into this, and give you a demo of what's possible now in the new version of the library that we released in June with a lot of feedback from actually the Stitch Fix team. So with that, let's kick things off. Just a quick overview of what we're going to talk about. So we'll just do a bit of a motivation of why we want to monitor and how do you analyze change in the machine learning applications. Things tend to be a little bit different in machine learning applications. How different are they, and why do we need special tools for that? Then we'll talk about telemetry, which is kind of the foundation of a lot of activities that you could do in the process of monitoring and analyzing machine learning applications. And we'll give an intro to whylogs, talk about some design principles of whylogs, and then do a demo, which is going to be a live demo, and that's my favorite part of any talk because it's both exciting and stressful. But I'll kick things off, and the most important thing I want to say is it's really fantastic to see your faces. I really appreciate that it's such an interactive event. And please do not hesitate to pause me anywhere if you have questions. I'm not bothered at all if you turn your microphone on and interrupt with questions, because these live discussions are always the most energetic and the most interesting. So with that, let's dive in. All right. So machine learning applications, well, kind of at the high level, I wanted to start with what it feels like to run machine learning in the real world. And, in many cases, people describe it like drinking out of the fire hose and being very frustrating. And there are a lot of things that could be happening to the machine learning application as it starts essentially serving inference on real world data, because real world data is really messy and it's nothing like the beautiful, well curated, clean data that is typically used for training. So what does it feel like running machine learning in production? Well, frustrating. And I think the main reason for that is because machine learning applications are extremely complex. Let's dive into what does this complexity entail. So first of all, if we kind of think about the concept of monitoring machine learning application as kind of a very simple activity. Let's analyze change in this ML application. If we break it down into a handful of kind of parts of the sentence, analyze change in ML applications or in an ML application. Let's zoom into the concept of ML application. Where can change occur? So there are, of course, features. It's either a feature pipeline or a feature store. That's probably one of the first early places where change can occur. So changes to how the feature transformations are done, changes to schema, changes to the underlying technology of the feature pipeline, all could cause all kinds of surprises in the actual machine learning application behavior. And then we have the model endpoint, which together with the features and the predictions kind of can be called something like model serving health. So what are these predictions that are coming out in the real world inference? How are they changing? How is the distribution of the predictions changing, and so on? And then once you have ground truth joining, you get a sense of model performance. So how is that changing? Is this in line with what you saw during experimentation or not, and so on? And then finally, you get the final customer impact. So the customer receives the prediction and that impacts them in one way or another, and kind of watching how that impact changes over time and how aligned it is with your expectation is another place to let's say monitor change. So already there's a lot of complexity about like where should we look for change. Now, if we think about what change means and how do we know if something is changing, again, a lot of interesting complexity arises. When we typically think about looking for change, we need to establish a baseline. So change with respect to what? And in machine learning systems, it's especially interesting because in most cases, your baseline is your training data, which is something that happened in a completely different system, probably many, many months ago, maybe even by a different group of people than the one that is launching the model and running the model in production. So establishing kind of the baseline of against which we're going to be measuring change from this training stage, or establishing the baseline from the data that we have already ran predictions on and have some ground truth on, again, creates additional complexity, because in addition to just saying, let's compare to what happened yesterday, you already have quite a few additional requirements, like let's compare the model behavior to, or let's compare, let's say, the inputs into the model to what we saw during training, or let's compare the model behavior during what we saw during evaluation. So even more complexity. And then finally, how do we measure change? And when it comes to machine learning, again, this how is a little bit different. And I think the biggest difference from kind of traditional sense of monitoring and measuring change is this concept of data drift. So, machine learning applications are powered by data, and as the distribution of data changes, the behavior of the machine learning models tends to change, or rather, I think behavior is a very esoteric term, but the predictions that the model is going to be outputting will be different if the inputs have drifted from what the model saw during training. So watching for data drift or concept drift, essentially differences in the distributions, is a very important thing to measure, and it's a very good indicator of change that might impact the model behavior. And then you'd want to measure things like data quality decay, model performance degradation, customer experience degradation. So again, a lot of things that we need to measure. So that drives essentially the complexity of this whole concept of, oh, we need to monitor a machine learning application to kind of quite a thing. You potentially started with one requirement that says, hey, I would like to understand how my model is doing in production. And maybe that's as simple as like, let's look at how this accuracy number changes over time. And then as you start kind of peeling the onion, you're discovering more and more requirements, and they get incredibly further complex. So one way to kind of start addressing this problem, and I'm, as an engineer in the past, I like to think about kind of design principles and what kind of foundations can we build to start solving this very complex problem of monitoring or analyzing change in an ML application. So that's exactly what we did in the very early days of whylogs. In 2019, we sat down with a few of our co-founders, and by the time we sat down to start designing what we'll build at whylogs, kind of a little bit of a history, we spent I spent 9 years. A few of my co-founders spent 5-6 years at Amazon, and there we built kind of tools for machine learning operations a handful of times, or rather, I would say we made mistakes in how we build tools for machine learning operations a couple of times. So when we sat down to think about how we're going to tackle the problem of monitoring for machine learning data at whylogs, we had very, very concrete wants and needs. And specifically, one of the things we've identified after a lot of whiteboarding is that when you're trying to monitor either data or machine learning application, the way you collect telemetry about this machine learning application is very distinct and very important. And it's very important early on to decouple the process of capturing this telemetry, capturing various statistics and vitals about how this application is doing, from acting upon it. And the reason it's important to decouple, well, there are actually many, many, many reasons, but you have a lot of control if you decouple the process of capturing telemetry. And this control allows you to, figure out how to capture telemetry in both batch and streaming systems, because that's one of the basic requirements. I imagine in Stitch Fix, you're running both batch workflows and streaming workflows. The last thing you want is to have a separate monitoring system for each one of them. And then you want to make the capturing process very model agnostic and very platform agnostic. You want to have control of how lightweight this telemetry capturing process is. And you want to really ensure that this telemetry that you capture is extensible, configurable, mergeable, and there's a lot of control about the process of capturing. And then you want to do a lot of things that have to do with acting upon this telemetry. So one way to think about this is, in the process of building a monitoring solution for ML and data applications, telemetry matters a lot, and what you do with telemetry matters a lot. So this was like a really long 6-minute intro into why we built whylogs. So specifically, when we sat down, we identified that telemetry is very, very important, and there's no telemetry capturing standard for machine learning and data application. So I'm going to unpack this a little bit and say, when I say telemetry, or you can say logging, or you can say profiling, what I mean is that you want to capture a unit of information about your ML or data application. And by unit of information, I mean you want to identify some kind of window of time or window of life. So window of time would be like an hour or a day or a week, or a window of kind of meaningful batch. So if your system runs in batches, so that would constitute whatever batch cadence you have. And you want to understand everything about lineage, schema, counts, summary statistics, distribution, et cetera, about this window or batch of time. And that would be your log or your telemetry profile. So that's specifically what whylogs allows you to do. It standardizes the process of capturing all of the possible data you might need in order to monitor and understand how your data and machine learning application changes over time. So it introduces this concept of logging all of the things you could possibly want to log or capture, all of the things you possibly want to capture about each feature in your data. And it makes it super easy to integrate in various places and super lightweight to work with. And it's open source. So that's what I want to spend majority of the remaining of the presentation. And I want to pause here, see if there are questions, ideas, thoughts before I dive into whylog specifics. No pressure. I could just be talking and everybody else is enjoying the talk track while checking their emails. Sweet. Okay, so diving a little bit deeper into whylogs, one of the key perks that you get when you separate the process of capturing telemetry from the process of analyzing telemetry is that you get now these log files, and log files are powerful. As software engineers, we love log files. That's basically the lifeblood of all of our debugging activities, right? So what if you now had a concept of a log file that describes all of your data vitals? There are so many things you can do with it. So if you just have one log file about, let's say, your training data, immediately you get things like data documentation. So you can capture statistical properties of all of the features in your training data, and you can just store it in some lightweight manner, and you wouldn't have to kind of rerun the data analysis on this batch of training data in order to understand what data was in there. Or you can do exploratory data analysis very fast. You wouldn't have to reanalyze all of the features. So that's already useful. Now, if you have two such profiles, so let's say you have a profile from that describes statistics about your training data and the profile that describes the statistics about a meaningful batch in your model inference time. Now you can compare them one-to-one and say, oh, okay, the distributions of these 5 features, let's say in my inference profile, differ from the distribution of these 5 features in my training data. So I could say that I'm observing some distribution drift in these particular features. Or if you want to stay within kind of the training realm, you can say, oh, the distribution of this one training data that I use differs from the distribution of this next training data, which I might have cleaned or have added additional data in such a way, which gives you kind of a meaningful sense of whether you improved or made your training data worse. And then when you have 3 profiles, it allows you to do even cooler things like continuous monitoring, because when you have, let's say, data over the past 2 weeks of how your data looks like, so let's say you have a distribution of every day of how a particular feature looks like, you could take a meaningful quantile from that distribution, and you can get a kind of a time series of how this quantile changes over time, and you can do interesting monitoring. You can do forecasting on this data, you can do meaningful thresholds on this data, and so on. So now all of a sudden, once you're capturing these profiles systematically, you create a view into your model inference that is time series based, that you can observe over time. And this statistics doesn't have to involve distributions. Kind of the most popular things we capture are counts, missing values, cardinality, and so on. So we'll dive into this a little bit deeper. Actually, in fact, this is just a really, really high level overview. So it's a human readable form of the statistics that whylogs could capture. And depending on the feature type, so if we have discrete features versus continuous features, you tend to capture different types of statistics. But the cool perk here is you essentially, with the default distributions, is you would capture well, pretty much all the stats you would need to do data quality validation and data drift understanding. And the extra perk is that you actually get density functions and error bars. So instead of just saying, let's capture, let's say, the mean of this distribution of this feature, which, is useful, but it's not aggregatable and it's hardly comparable. The statisticians in the room would probably frown upon that. Once you get essentially non-parametric distributions of the data in a particular batch, you can do really cool things, and you can do very true distribution drift comparisons based on like Hellinger distance or KS-test and so on. And another cool perk of whylogs is that the way we capture these distributions is using, which is going to be the core of the demo, is using stochastic streaming algorithms. And Jamie will talk a little bit more about kind of what are we basing this on, but the big perk is that because these algorithms are streaming algorithms, we can capture all of the statistics just with one pass, and you never have to sample. And I would say sampling is probably one of the hardest things that nobody talks about when it comes to doing both EDA or monitoring of the health of the data. But if you do have to sample, it introduces this additional challenge of, how do you sample? How do you maintain the sampling strategy? What do you do when your data naturally drifts? Do you have to change the sampling strategy and so on? How much accuracy are you losing? What happens to your long tail data and so on? So one of the big perks of whylogs is that everything gets captured with streaming algorithms, so you only do one pass over the data, and because of that, you never need to sample. So we're working with teams that process terabytes of data daily, and they run this inside their main data infrastructure. They don't create another cluster, and they essentially just pass the data that flows through their model inference or through their feature pipelines through whylogs, and they capture all these profiles, and they don't need to maintain additional infrastructure or sample, which is really powerful. And then another big perk of whylogs, and kind of big perk of thinking about ML telemetry and data telemetry as an open standard and getting feedback from teams like Stitch Fix, is that we could really simplify the API, because again, as software engineers, we're really used to very simple logging approaches. So you shouldn't be thinking for 20 minutes or for hours or for days or having meetings about what to log and how to log. Logging is a pretty natural thing to do in software. And if this could be simplified down to one line of code, you would be a lot more encouraged to do logging. And if it's really cost effective, really there's no reason to not log. So what we've done in whylogs is we've built in log rotation. So essentially you decide what's your logging cadence, and you don't have to worry about this log rotation. And then we really simplified the interfaces of logging various types of data. So everything from your data frames to images to text, which is in beta. So if you have text use cases, would love to get your kind of wish list of what types of things you would want to log for text data. But the idea here is, as you see in this very simple code example, you don't specify any configurations. So you can either rely on the default configurations that whylogs provides and essentially says, okay, so if we're dealing with images, these are the statistics that will be logged. Or if we're dealing with a data frame, if we have continuous data, this is the statistics that will be logged. Or if it's discrete data, this is the statistics that will be logged. Or you could essentially specify the configurations for what will be logged based on a data type. And these configurations, are shared with the rest of the team in code. So the configurations are specified in code, so you can create standards across your team or across your organization and how to log and what to log when it comes to logging data. So another important aspect of whylogs, which is something I highlighted earlier on, is your machine learning pipeline or your machine learning application is very complex, and you want to log things in many places, in your feature pipeline, around your model inference, at the place where you join the predictions and the ground truth and so on and so forth. So one of the big perks of whylogs is that we could build integrations of this very simple concept of we will stream the statistics and calculate, we'll stream the data and calculate all of the necessary statistics, and we can integrate it with a wide range of different tools and architectures and data solutions and cloud services. So this is just a really high level view of what we currently work with, and we're constantly adding new integrations. I think the interesting highlight is, and again in the demo we'll do a little bit of a deeper dive into this, as whylogs works with Ray, with Kafka, with Spark. So it's really friendly to all your distributed and streaming workflows, which is very rare for a library that analyzes data distributions. Typically, you're required to centralize your data somewhere in order to process it, and that creates quite a challenge, because if you're working with large volumes of data or distributed applications, all of a sudden you have to maintain this very complex infrastructure of siphoning your data into some kind of data store. Okay, and finally, the big perk of whylogs is you wouldn't have to, again, siphon your data somewhere to post-process and extract all of the telemetry, extract all the statistics, because it benefits from the stochastic streaming algorithms and really cool algorithms that are based on a data sketches library, which we're going to dive into in a second, which allows you to capture all of the statistics in a way that scales with the number of features rather than scales with the volume of data. And it also benefits from essentially a nearly constant memory footprint. This is really awesome because you could essentially add whylogs into your existing data infrastructure, and effectively what it would do is add a small overhead to your existing workloads, and you will get all of the statistics that you would want to get for any kind of testing, monitoring, or analysis. All right, so I got you all excited about whylogs, hopefully, and I would love to pass over to Jamie, and maybe before Jamie, as Jamie is switching over, if anybody has questions, but Jamie would give us a quick overview of the demo of what's possible with whylogs, and a little bit more background on how does this magic actually work.
Sure. You want me to start out with just the overview kind of thing there, or is there questions?
Let's see.
I had a question, although Jamie might be gotten to in your sort of more details. You mentioned minimal overhead. I'm kind of curious of the, like, logging in a batch setting. It's like, okay, who really cares about the overhead? Logging in an online, like, super low latency setting, I'm kind of curious how that contributes to the overhead, and what the recommended sort of architectures are for that. So.
Yeah, so we could talk a little bit about that. I was going to cover it in this demo, but we have two modes, and almost all of our investments in optimizing for efficiency were around the batch scenario, because that tends to be where it was easier to optimize things, and we had more customers asking for a massive scale of data processing in that context. For like real-time inference, we have two different approaches, and I think most people have used this first one, which is used a whylogs container that processes the data, and that's done as part of our just like a general integration approach. So you can isolate that and make it a little bit easier to manage how you scale that out, since those tend to scale horizontally fairly easily. The more like in-depth integration is, in proc with the web service. And having worked on Amazon and retail websites, like it's very bad to lower the latency of returning a customer-facing thing even by a few milliseconds. So you'd have to take a lot of care to make sure that you're not impacting those systems. It's probably worth a whole nother talk to go into that that topic. So I've seen people do things like have an asynchronous processing of the data from a web request. So they're processing the incoming data. You have maybe a JSON packet or something that whylogs can handle, like a dictionary of keys and values. And if you use like a rolling logger, it will aggregate data as it comes in a streaming fashion. And then the trick is just not to spend time serializing or even doing the processing of those statistics before returning that back to the user.
Got it.
But we can talk about that. Maybe that's a good
That sounds
follow-up.
fascinating. To be clear, we actually use it primarily in the batch context.
Yeah.
In which case, optimizing to an extent, like I think Ramandeep's done some work on this, a decent amount matters, but it's like the degrees of optimization are totally different. So interesting.
Yeah, but I think one thing that's really fascinating about data sketches, which is what whylogs is built on top of, is this idea of mergeability, because it lends itself really well to both a batch, a MapReduce scenario, or just a scaled out web service, where you don't have a start and end to your data, and you always want a valid rolling window that's aggregating statistics that are valid, and then you can merge them across different machines in your fleet to get like statistics on the day. I'll try not to digress too much. I also
have a question that maybe is also answered by the demo. You talked in some of the slides about like data unit testing and like the anomaly detection and that kind of stuff. Are you going to go into like those sorts of models, how they work, or is that sort of the expectation of once you use a tool like this, you then kind of build some of that stuff yourself?
Yeah, I'll try to cover some of that, at least from a high level, and we can drill into specific topics as we have time. Let me do this, trying to share my screen. I don't have a fancy set of slides. I'm just going to try to do the really fun live demo and see how things go. All right, so a lot of the motivation on the redesign of whylogs from our V0 to V1 was about getting better efficiency and more configurability. So these are just some benchmarks if people are interested in that are a little bit more polished about setting up good infrastructure to get reasonable numbers. It's not, even this is not optimized very deeply. It's really just trying to get a clean cost of how much compute cost it would take to create those statistical profiles of data with whylogs. So in practice, there's a bunch of noise, and it depends on like how fast your cluster is to spin up and all those good things. So people are interested in that. We'll put links to all these things at the end of the talk, and we can go into more of those there. Not that one. All right, my cluster, I just want to show a little bit about another thing we try to do is in whylogs v1, the Python library is completely isolated. It doesn't depend on a specific jar or Java definitions. So installing it, I just have a Databricks cluster here, is as simple as like saying you want to install a new library, pointing to PyPy, and you can say whylogs. In this case, I have to install at least the Spark extra. I would suggest probably Spark and wylabs kind of go well together in this context, but you don't have to do that. I've already installed like a overkill amount of extras just in case we wanted to do stuff. And this is my test cluster. I have taken away all of the state. So this is a brand new cluster. I'm just going to hit run all because it takes a little while to go through it. And then we can kind of talk through the different things here. This test was actually inspired by some initial perf numbers that Ramandeep had shared a while back. And one of the things I wanted to do is create these test files that we could, anyone on my team could deterministically try a new build on. So I created just not very excitingly named like data frames, 1 through 4, based off of these different dimensions of rows and columns. One thing that's to note is we say things are lightweight, but anyone can say that. One thing that's maybe important to note is that most of these algorithms are designed to be memory bound or logarithmically growing with some cap. So it's really just a space and error trade-off. You can give a lot of these algorithms, such as the KLL sketch that tracks histograms, you can give it more memory to have slightly lower error bounds if you want that, or you can shrink it down if you want it to be a little bit lower. And every column that we track that's a numeric value will, by default in whylogs, get a KLL sketch tracking it so that you can do distributions on that data and do those fun things like Alessya said, where we can compare across time and get a distribution from yesterday and ask how far away is it from the distribution of the data today on this numeric column. So if you have a very large number of columns, it increases the size of the data of the profiles. This data set here is my data frame 3, it's around 73 gigabits. And
Jimmy, can you zoom in just a tiny bit?
Sorry, yeah, is that working for people?
I think that's better, yeah.
Yeah, all right, good, thanks for that. I guess I can get rid of this little side panel too. So this test data set's just stored in Parquet, so I'm always reading it. And well, I actually don't need to expand it there. We can look down here. It doesn't have very interesting named columns. I just have string values 0 through however many columns there are. In this case, I think it's 119. Yeah, so 0 through 118 are the labels. Each one is a double, which is actually kind of the worst case for whylogs because we have the most interesting and the largest number of different statistics on fractional values. There's some statistics that only make sense on categorical values, but we have a little bit additional and larger memory sized statistics that we gather on doubles, such as cardinality sketch, the KLL sketch, what I already mentioned, as well as like just counts and normal summary statistics. So we thought, like, even though this isn't that realistic, it's a very reproducible sort of kitchen sink kind of test for us. And these are just random values that I generated between 0 and 1, so they're not particularly interesting, but it does give us a nice way of checking if some of the algorithms are correct, because I would expect the quantile for median to be near 0.5, for instance. Depending. So this, all right, so this data set, data frame.count just returned, that was surprisingly fast. And just to show the size of the data, if I'm trying to highlight by the 3 zeros there, it's hundreds, thousands, millions, so 83 million rows and 119 columns. This is our main entry point in whylogs. It's kind of experimental because all we're doing is we're taking that really simple y.log statement that Alyssa showed earlier, and we're putting it inside this PySpark hook that that PySpark exposes for a pandas UDF. So I can define a Python function, and then the PySpark system will do some helpful like map reducing. And basically, if I write a function that can operate on an iterator of pandas data frames, then I can execute it without having to think about the map reduce too much. If you are really interested in optimizing this, you can do better than I did. And I'm a little embarrassed that I haven't optimized it more since the initial launch, since it was kind of good enough to get the pattern down. Oh, it already finished. Okay, so this collect data set profile view here, I just give it a pandas data frame, and then what it returns back is a whylogs data set profile. So this data set profile should be about 3 megabytes, I think, in this case, it's one of the larger ones, for the 73 gigs of data. And it took 1.3 minutes to run on this cluster, so it's not too bad. If we want to kind of dig into what it was actually executing, you can see that the underlying file here had 687 partitions. So as long as you have enough partitions in the data, and I'm not having more machines or more cores in those partitions, it will parallelize the execution of this. One thing to note is, like, if you're executing things in Python, right, you have a lot of people run into this where it's mostly single threaded unless you use some framework or you do some fancy library to get you multi-processing. So a lot of the just straight up naive execution of data is hard to scale out on and hard to make use of the machine resources well. In this case, Spark will spin up a task per processor, so I don't have to worry about that, which is nice. And it just uses that pandas UDF to create a profile for each executor node. And because they're mergeable, this collect dataset profile, notice it has a collect in it. It does two things. It has a whylogs.log inside that map function, and then it has a collect that just merges them back. And it can pull them to this driver here, because even though the data wouldn't fit on the driver, the profile is relatively small. Here are some of there's this helpful 2 pandas that we provided just so you can see what's in there. I wouldn't recommend actually using this other than just a data exploration kind of way. I'll talk a little bit about different ways we can use the whylogs dataset profile here in order to do data quality checks or to do drift analysis and things like that. I'm going to pause here. If anyone has any questions, just throw them out. Otherwise, I'll just show some of the statistics we have here. So in this case, this distribution is one of the metrics that we gather by default on floats or numeric data types. And we don't actually have this like Q01, Q05 hard-coded internally. It's collecting its own efficient representation of a probability mass function. And it's only when I ask the sketch for a specific quantiles will it serialize it. And it's kind of a, so this is like a lossy operation I did when I ran 2 pandas. And it just outputs some default quantiles. You can actually ask it for any quantile you want is the other nice thing. So if you really cared about the 0.98 or something in your business case, that will be something you can retrieve from this sketch with the same kinds of error bounds you would get from the other quantiles. And you can see there's also this n is just a count of how many elements of that type was processed by this sketch. So in the distribution case, we would skip strings and other things like that. So this is all numeric. There's no missing data. So it's the full 83,000,001 because my test generation was off by 1, like a scrappy dev tool it was. But it lets me check that I counting right. You can see the mean here is really close to 0.5 because these are randomly generated numbers. The max is probably rounding to 1. It's not actually 1, it's something very close to 1. Questions? I'll jump into.
Let's see some cool constraints and monitoring features that
so all right,
was
great.
asking about.
We've processed gigs of data, and what do you do with it? I say it's relatively small. So the nice thing is I can run analysis on my executor node, or I can stop this cluster right now. And I'm not going to do that quite yet, but I could maybe scale it down. It should auto scale if we have that turned on, and then you're not using everything that we did to do the profiling in the MapReduce step. But we can do things like create constraints. Constraints are just a declarative way of defining some data quality checks. There's kind of 2 things in whylogs in the open source side that we can use to define how we want to detect problems in the data, whether it's drift or if we have some rules that we want to apply. Like if we are running on like FICO scores, like we have lending club data set, we know that they can't be above a certain number or below a certain number. We could define those kinds of things. Another one we can do, so the 2 ones are these constraints, and then there's a constraint builder which will let you create expressions on the columns of the features that you have and the metrics that are defined by this profile run. One thing to maybe point out is these constraints are constraints on the metrics. So if you want to do something new and interesting, you might have to create a custom metric to count something, and then you could say that count has to be below 1. Like if I wanted to have a PII detector or something like that, I could have a regex that counted the number of times an email pattern was seen, and I could then write constraints on top of that. So I think this pattern can be very flexible. It's a little bit tedious to set them up. So this is the scrappy way you would do this without wlabs. And in this case, I'm just showing that this constraints builder is taking in the profile that I generated there. And what that will do is it will just make available all the columns and the metrics inside this builder object. And then I can select different columns, and we can create constraints on this. This just shows, like, if you wanted to know like what kinds of different columns there are, they're the boring named ones of the numeric values, and the kinds of kinds of metrics that we have here is types, which is a count of types, cardinality, distribution, and just overall like row count kind of thing. So in this case, I'm going to use the profile to pull out the column, the first column, this column 0, and I'll from that column get the metric for the distribution. And just calling toSummaryDict is another thing you can do on it to get a dictionary of all the keys. Again, this is unwrapping that probability mass function and giving us specific quantiles, similar to the 2 pandas, but just to kind of see what's inside that metric. And we could write constraints on any of these things. So down here, I said, here's 3 different other values that we might use to make constraints. So I executed them as like, there's 83,000,001 rows. The average is very close to 1/2. The max is very close to 1. Great, that's not too surprising. And here is an example of a selector that says, I'm going to create a constraint on this metric in this column. So I have the selector here, and then what you can give it is a condition. So in this case, partly why we do this is we want to make it flexible so that you could have a selector that said on all columns, or that said any distribution metric, all my values should be greater than 0. So you don't have to bind this to a specific column or a specific metric, but you can. In this case, it's kind of a simple selection where I'm just saying it's distribution on the first one. And I'm going to say that the average has to be under 0.6, which it should be unless my data is very skewed if it's random. The median is above 0.4, which it should be because it's random and they're large enough. The median should be close to something around 0.5. And then I have the max, which I expect to be very close to 1, should be like this. So if my profile was small and it was random, this might fail. And we can see that these are different constraints that I've then added to the builder down here. So I gave it a friendly name, and I have the column median above X. Partly this is so you could reuse it and you could parameterize this just to show kind of a cookbook of how you might extend these. And then from the constraints, if you call build, it outputs this object called constraints that you can then evaluate on any data set. So if I had a data set profile, so if I created this definition of what I think is valid, I could profile my data again and again. I don't have to bind the profile to this constraints. I can call constraints.validate and pass in a profile if I want, and it will give me this little report. It's not particularly interesting here. This is just sort of the API. It gives you the name of the constraint and how many times it passed or it failed. In the case of these, they all can only pass or fail 1 time. So these all passed. This is not really great UI, as you might be noticing, but it just shows how you could use it. If you want to hook in, we have some visualization. So this is using the notebook profile visualizer, which has some drift detection and tools in it there that can be used programmatically, kind of like above, or just to show like if you didn't want to have this be plugged into a Jupyter notebook like UI, you could run this in your own code to get out what's failed or not, but you can also just spit out this report. We can also, like, I think this is one I was like, well, maybe I can make this a little bit incorrect. So this one is saying, all right, I have that same add metric constraint. The column 0 needs to be between 0.95 and 1, and just tighten it a little bit. I know it's really close to 1, so I expect if I run this again, we would get one of them failing. And if I run the report, hopefully we see that last one would fail because the value, as we saw above, was very, very close to 1 that had multiple 9s in it. So just to show you kind of what that UI looks like. And if you built this up over time, you could have, thousands of checks here, and you could query from them and things like that. The other thing I wanted to show is just to prove like what's the size of this profile. We wrote it out, so it's 3.2 megabytes in this case. And if we want, it's pretty easy to write to whylogs. So here's maybe the scariest part of the demo, just to show you what it looks like. Because I think writing constraints is interesting, but you kind of have to build up some infrastructure to determine and mine your data, like either a trailing window or a reference profile. Maybe you have training data that this is good data, and you could build constraints from that programmatically and apply them. But it's only our biggest integrators that have resources to build that kind of thing. Otherwise, you get kind of an out-of-the-box sense of monitoring from whylogs. So this won't work yet because I have to go create this model 36, and it won't let me get that. Okay, so this is our project dashboard where all different models go. I'm going to create a model. We'll create, anybody want to give it a name so it's real?
Stitch Fix. Algo our demo.
Okay.
I will
That's a long name
because we have
okay.
7 minutes left, so
okay,
I want to make
go
sure
fast.
we run through it.
Create it. Hopefully that got created. If I go back to just the project dashboard, it should say there's no data in it. So that's over here, this project Stitch Fix one. And if I go back to my Databricks and I uncommented out this whylogs write, by the way, there's some other like OS environments I set down here, the API key and org ID and things like that. And there's this, we'll link to it, a notebook that shows how to do this programmatically. Then when I like show those all right here. So if I run this, let's see how long it takes. It's, yeah, so about half a second to upload it. So status true. And if we go back to, hopefully if we refresh this, we'll see some of our data up here. Dev environment, it's always a little iffy. Okay, so it says 119 inputs, and it has the data for today. Great, so this shows me all the columns, and this will give me all the standard metrics here. If you do this every day, we will have, like, their default monitoring is really easy to set up out of the box. It's just presets saying like use trailing window, whatever time you want, and it can detect anomalies, whether it's a distribution drift in numeric features or categorical features or things like that. This is just 1 day of data. So I also created a separate model here that just did the same thing, but played it back over 7 days. So this is the same kind of random data, just to show you, like, my favorite is the looking for drift in quantiles based off of the distributions here. All right, only a little bit of time. That's kind of like my quick speed ahead portion of the demo. Questions, right? Anything we want to drill into?
Yeah. Can you go into a little bit more about how you do like the anomaly detection, or like, I guess things deeper than just like if this value is higher than that one?
Right. So I think, go ahead, Alessya.
Maybe I can jump on that.
Please.
So if you click on Monitor Manager really quick and just go into any monitor just to give an idea. So when it comes to whylogs, the type of monitoring anomaly detection you can do is kind of up to you. So we have the whylogs as a library standalone provides you with kind of these profiles that then you can do cool things on. And within whylogs, the types of anomaly detection are really kind of simple constraint-based things that, you know, you can auto-generate constraints. That's probably the coolest feature in the open source. Now, when you are generating these profiles systematically, you can do much cooler things with anomaly detection. So the types of, so if you click custom monitor, and I want to just talk about the different baselines. So go a few steps to the baseline. So the different types of baselines that you can now support with anomaly detection could be things like use my training data or reference profile from some other activity, or use a window of time from some time in the past when I did generate these profiles, or use a dynamic 14-day window as a baseline. And you can set these baselines up for either your distribution drift detection, or for data quality verification, or for performance metrics. So and we didn't touch too much on that, but in addition to just looking at the inputs, you could also essentially sketch your performance data and also monitor how your performance changes over time, you know, accuracy of one score, et cetera, et cetera. And for more complex things, which we don't surface in the SaaS, we can essentially, if we do have about 30 days of your data distribution history, we can do cooler things like seasonal forecasting of what the value should be. So for a lot of our customers that are in retail or logistics, they have very, very seasonal data. And for them, we can essentially train, could be something as simple as an ARIMA model, but pretty powerful, that would essentially identify when you have seasonal anomalies in your data. And then so this about high-level anomalies, and then you can do outlier detection as well. So when you do have a distribution, you could essentially do outlier detection with constraints and so on. So does that?
Yes, thank you.
Sweet. And what Jamie was showing us with whylogs, essentially getting these profiles into whylogs to kind of see what types of monitors you can configure. Whylogs has like a free tier, so anybody can just go create an account and try it out, kind of see what these whylogs profiles look inside. Thank you. And Jeff, I see a hand up.
Super quick. I just want to, I think I'm understanding sort of how the algorithms work, but like, let's say for some, reason I wanted to capture, like, okay, give me the distribution of your random number generator, but like only for values lower than 0.5. like I could set up some metric that's like the value of this metric, but only if the underlying thing is lower than 0.5 or whatever. If I like after the fact, because if I'm getting this right, like this is capturing the sort of summary statistics, but not the underlying data. If after the fact I was like, oh, you know what? Actually, I wanted all the values under 0.25. Like there's no way to do that like automatically, right? Or like what is the sort of like there's no sort of playback function in some sense where I could like retroactively create a metric that I'd have summary statistics on even like after the fact.
Yes, no, unfortunately not. So you kind of have to commit to the description of the statistics that you want to create. One way to kind of bypass that is because it's so relatively lightweight to do that. You can create a few different versions depending on your use cases. You can say, oh, I want to keep, distributions of the values that are, greater than 0.5, and then distribution of the values that are greater than 0.2, and so on. So it's relatively lightweight to capture this data, but yes, you do have to commit to kind of this more or less standard sense of what types of stats you're capturing.
Also, just throw out, there's a complex, too complex to show here, but we also have this idea of segmentation. So if you know that you might want to split up your data off of some numeric value into values that are less than 0.5 and above, you can say there's two segments, one for the lower half, one for the top half, and you'll get, because you can merge those, you'll still get the overall statistics here, but you could look at one segment or another. Caveat that it costs more to profile that data because you're creating two different data set profiles for that same data set. So you can't do it without taking some care to make sure you're not exploding the cardinality there. But we have people that, you can also define filters there. If you really didn't care about a large number of different segments, but you said, you wanted to only log one very specific segment that's highly selective and compare it to the overall data, you could do that as well. I'll stop sharing.
All right.
Unless.
I think we are at time, but I wanted to just say a few really, really quick things. I think I'm sharing.
Oh, yes, you are.
I think I'm sharing the right window.
Oh, yeah, thanks.
So we have a bunch of resources and we'll send these slides over, but most importantly, again, giving a presentation to the wonderful Stitch Fix team, which has already been an amazing contributor to this effort. We really think of whylogs as an open standard, and open standards only get better with community input and with community contributions. So it's very easy to give it a try. Here are some links, and again, we'll send the slides over to make it even easier. And it's also easy to contribute. And if you don't have time to contribute, but have feedback or ideas or wish lists, there's a Slack channel that you can join, or just open GitHub issues for things that you would find really valuable to see implemented in the library. And we'll certainly work on it. We have a dedicated team and a really vibrant community. So super excited to see what kind of features or ideas you'll come up with.
Yeah, thanks.
And that's it. And feel free to get in touch with either myself or JB. Again, would love whylogs users and would love your feedback.
Awesome. Thank you so much, Alyssa, and also Jamie for the amazing talk and the demo. And thank you everyone for joining the session. We'll share the slide and then also the recording afterwards. Cool.
Thank you so much. It's been a pleasure and really great to meet some of the team members.
Yeah, thank you guys.
Thank you all. Okay, have a good one.
Thank you.
Thanks so
Bye.
much.
Have a good one.
Bye.